this is an announcement for the participants. Professor Kembhavi's lecture tomorrow afternoon has been shifted to May 30th at 4 p.m. The rest of the schedule remains the same. We have already 100 participants who are online, so you can start whenever you're ready.
Okay, all right. Thank you very much. So, good afternoon. So, I'm going to be talking to you today and maybe the day after tomorrow also on white dwarfs. So, I have 5 lectures in all. I thought I had 3 lectures. Yesterday, I found that I had 5 lectures. I intend to divide them mainly between white dwarfs and black holes. So, the black holes part is called black holes across their mass spectrum. Now, I'll begin with white dwarfs. And I have chosen this topic because it's a very beautiful combination of astronomy and physics. It has got very important results. And there's a lot of work going on in the subject even now. Now, you may think that white dwarfs are old. To some of you who know about white dwarfs, that some of the most famous work on it was done in the late 1920s and early 1930s. And the Nobel Prize for the work, Chandrasekhar's work, was given in 1983. So it seems that it's a thing of the past, and why do we need to go into it now? I hope to draw your attention to the beauty of the physics and some of the current work which is on to show that this indeed is an important topic. It's quite ridiculous talking like this to you people. You're sitting all over the country, and I'm sitting here in my living room and giving you the talk with no contact with you. The good thing about it is that so many of you can participate. The bad thing is that we can't really see each other. Now, for example, I would like to ask you whether you know what is the Hertzsprung-Russell diagram. And if I was sitting in the hall, I would ask the same question. If I was speaking in a hall, I would ask the same question. And about 4 of you would have said something. But from the expressions on your face, I would know how much you know about the HR diagram. Now, clearly, that kind of communication is not possible through this remote learning and teaching. But we'll make the best of what is possible. So now, a thing like white dwarfs requires many different concepts for astrophysics, and not all of them would have been covered in the week or so that you have been having these lectures. Not many of them, in fact. So I'll make the lectures more or less self-contained, which would mean there could be some overlap with what other people are doing. But that sort of an overlap is always very useful because it acts as a revision, and different people have different ways of saying these things, and also the concept can change a little bit with the context in its interpretation. So, given all this, I won't worry too much about repetition. So, what am I going to be covering here? So, first we'll talk about the discovery of white dwarfs, which in itself is very exciting. Then I'll quickly explain to the Hertzsprung-Russell diagram very, very briefly. Then I've said here the problem with white dwarfs, but on reflection, I find that I should take that up a little bit later. What do I mean by the problem with white dwarfs? Is that the physics of them can be very confusing, and Eddington and other leading workers at the time were sort of led astray because of that. But in order to explain to you what was the problem that they faced, I think that I should bring that topic up a little bit later in the lectures. Then I'll talk about white dwarf theory and the Chandrasekhar limit. Then I'll go to stellar evolution very briefly again to talk about, to say how white dwarfs come into being. Then there is again the very beautiful theory of white dwarf cooling, and then white dwarfs as progenitors of supernovae type 1a, which, as you know, are very important distant indicators and have led to and have helped in assembling our knowledge about the accelerating universe. But these are just some of the problems. I mean, after all, not deal with them as I go along. All right. So now the discovery of white dwarfs. So you see, what we call the classical white dwarfs means that these were discovered in the beginning of the 20th century, and these appeared to astronomers as a compact, high-temperature star. So star is in inverted commas. Everybody thought it's some kind of a star. Now technically it would not be a star because a star could be is an object which generates energy through nuclear processes. Again, it's in the process of doing so. White dwarfs, in a sense, are dead objects. They are beyond the stage of nuclear generation of energy. Now, three such objects were discovered early in the 20th century, and one of them, the 40 Eridani B, is a member of a triple system of stars actually in 1910, and then Van Manen which was by Van Manen in 1913, and the most famous early white dwarf, Sirius B, whose properties were established over a period of time between 1910 and 1950. Now, Sirius B is a member of the binary system, with the other member, the main member of the binary system, being the star Sirius, which is the brightest star in the night sky. Then all three objects which are discovered were within 5 parsec of the sun. As you may know, a parsec is about 3 light years, so 15 parsec of the sun. So the fact that these three unusual objects are so close to us means that their density in the galaxy is quite high, and there will be many, many such objects in the galaxy. Right, so here are pictures of these objects. So you see that this is the star Sirius A, and here you can see the prominent diffraction spikes because it's such a bright star. And then you can see this tiny little thing here, which is Sirius B. So this is Sirius A and Sirius B. You can see that inside the circle there. And then here is Van Manen 2, and then which is a member of a triple system. And there's all sorts of things on my screen. Yes. So you can see here the white circle with a white dwarf there. So these are the three early white dwarfs that I just mentioned. It is, of course, currently quite easy to find white dwarfs. For example, you will see that this is an image of a globular cluster taken by the Space Telescope many, many years ago. And then the small little portion here is zoomed out, and the tiny dots inside these circles, white circles are there only for reference, and the tiny dots, each one of them is a white dwarf. Right, so you can just discover many white dwarfs very easily now, because you know the properties that these white dwarfs occur in great numbers in objects like globular clusters. Right, so now what are the properties of white dwarfs and where are they? And one simple way of doing that is to put them on what you call the Hertzsprung-Russell diagram. And I'm sure that this diagram must have been mentioned to you or you're familiar with it through your earlier reading. And what happens in the HR diagram, which clearly is the most important diagram for stellar studies, for the understanding stars, and this was again done in the 1910s, independently by Hertzsprung and by Russell. So you see on the x-axis here, you have got these letters O, B, A, F, G, K, which tell you what is the spectral type of a star. So each star has a spectrum, which is mainly made up of absorption lines. And then by looking at the pattern of the absorption lines, you can classify them into these main classes. And each main class is divided into 10 subclasses and so forth. Right? And these classes, and when the diagram was first made, these patterns and these classes had been discovered. But what was not clearly known at that time is that there's a correlation between this classification here and the temperature of the star. So if you look at the top of the diagram, there you got temperature, and the temperature increases leftwards as you see. And on the y-axis, you've got the luminosity, which is the amount of energy which is emitted per second. And here the unit is taken as the luminosity of the sun, which is 4 into 10 to the 33 ergs per second. So these stars here will be 10,000 times as luminous as that. And on the left-hand side, you have the absolute magnitude. The absolute magnitude is somewhere here. It is being hidden by this thing. Yeah. So you can see the absolute magnitude is minus 2.5 log of the luminosity plus a constant. Right. So the higher the luminosity, the more negative is the magnitude, and you can see that happening here. And this is called in the HR diagram. You see most stars and majority of the stars are along this particular trajectory, which is known as the main sequence. Right. So and then you have got here stars which are known as giants, and then you have got the supergiants, and then if you look at the white dwarfs, uh, if I go to the if I go to the next one, you can see the three white dwarfs. So they are here in the lower part of the diagram. Okay, so the diagram itself has many more white dwarfs than just the three that I talked about. So what is the significance of the white dwarfs being down here? And for that you have to you consider the equation that you have got. You could I'm sorry, this is the wrong thing. It should be 4 pi sigma t to the 4 r square. Okay, so what happens is that you take the radiation which is coming from the surface of the star. The surface of the star can be approximately assumed to be at a certain temperature, and then it emits as a black body, and therefore you have got the Stephen Boltzmann law that, and then it has got an area of 4 pi r square. So L is equal to 4 pi sigma t to the 4 r square. Right. So now you see here that you just compare a star which is at this point with a star which is at this point. This star has got the same temperature as the star here. Because you see, this is, if I draw a vertical line, it's a trajectory of constant temperature. But then, but the luminosity of this one is much higher than the luminosity of the object here. So which would mean that the radius of these stars must be much greater than the radius here. And which is why they are known as giants, and here these are known as supergiants. On the contrary, when you come to white dwarfs, so you say that these are way below the main sequence. So which would mean that because a point here and a white dwarf here, star here and a white dwarf here have exactly the same temperature, and but then but this has got so much lower luminosity, right? And how much lower luminosity? It's a 10 to the this 10 to the 4, this is 10 to the minus 2 by a factor of a million. Okay, because 15 magnitudes, there's a factor of a million. But this luminosity lower by a factor of a million, the temperature is the same, which would mean that the radius must be very much smaller. So it is therefore clear that white dwarfs are much more compact than the normal stars. So this becomes very embarrassing. Okay, in the sense that you find that the physics as you know it really cannot apply to these objects. But we'll come to that. So here is how Sirius A and B were discovered. This is very distracting. On my screen, I keep getting these panels. I'm afraid to actually get rid of the panels because, yeah. So what happens is that you got the orbit of Sirius A uh, was being observed by Bessel, and this is the same mathematician Bessel of the Bessel functions. So in those days, many mathematicians did astronomy too on the side, and then particularly positional astronomy. And then you see that Bessel had followed. We don't have Bessel's data here, but if you actually look at the data from 1900 to 1990 or so, you see that Sirius A is periodically changing its position in the sky, which tells you that it is in orbit around one more second object, and the binary nature of Sirius was discovered by Bessel. Okay, and then, but the companion was first observed by Clark in 1861. Right, so you can see the orbit here. Now this is Sirius A and this is Sirius B, because Sirius A, being a much bigger star, has got the orbit with a smaller radius, and then you can see that they're going around a common center of gravity and so on. And therefore, you are established the existence of a binary companion, and which can be observed using a faint telescope. And then you can see here a picture of Sirius B. Right. So, what are the properties of Sirius B? Is that the mass of the white dwarf, I'm just calling it a white dwarf, it took some time for the name to be established, was between 0.75 and 0.95 solar masses. So, how do you get this? How do you get these masses? Now, that comes out of the fact that this is a binary system. So, you can apply your all the orbital laws to the binary system, and then you get the mass of the system. But if you actually try to do it, you will find that there is one unknown there, and that unknown is the inclination angle. Okay, meaning that the binary, you know that will always be in a plane. Now, if you draw a normal to that plane, so if that normal to the plane is exactly along the line of sight, then you will see the correct objects of the two stars in the sky. But just imagine that the normal to the orbit is perpendicular to the line of sight, then you'll see that the orbit is just on a straight line. Because you'll be looking at the orbit completely sideways. In general, there's an inclination angle, and that inclination angle comes out in the measurement of the mass. Now, then, how do you solve that problem? You can solve that problem if you get independent data on the thing. Like, for example, if it is both what's called a visual binary as well as a spectroscopic binary, and sometimes or an eclipsing binary. And because of the eclipsing binary, it means that the angle of inclination is quite small. So it's close to 90 degrees, in fact. And therefore, you can put sin I is equal to 1. So with this kind of conjecture, you will find that the mass of Sirius B is 0.75 to 0.95 solar masses. Now, the distance to Sirius A is very well known, and therefore it's a relatively close star. And then, therefore, since you know the flux, you can measure the luminosity. And we have already seen that the luminosity of white dwarfs are very small. So even though the mass of this object is comparable to the luminosity, to the mass of the sun, the luminosity is just 1/360th of the luminosity of the sun. So this is very surprising because we know now, though it was not clearly known at that time, is that roughly speaking, around the solar mass, the luminosity goes as around the third power of the mass. So if the mass is the same, mass is close, the luminosity also should be close. So this luminosity is significantly lower. But then, as I have already shown you in the Husband-Russell diagram, the temperature is pretty high. So how do we know the temperature? We know it by looking at the spectrum of the star, analysis of the spectrum of the star. So the temperature is 8,000 Kelvin. So if I invert the Stephen Boltzmann law, then I'll get the radius of the object, and which turns out to be 1.9 to 10 to the 4 kilometers. Now, as you may know, the radius of the sun is 7 into 10 to the 5 kilometers, so this is significantly smaller than the radius of the sun. Now, while this was going on, a very interesting thing happened. Before that, what it means is that the density of the gas, the density of the material in the star, is you just take the mass divided by 4 pi by 3 r cube, and you'll come to the startling conclusion that the density of the material is about 4 into 10 to the 4 grams per centimeter cube. Now, this is actually an underestimate. Right, then in 1926, Adams realized that because this is such a compact object, the gravitational field at its surface must be quite high, and therefore one should be able to measure the gravitational redshift, which was predicted by Einstein on the basis of his general theory of relativity. So he actually carried out a thing and got a radius which is close to this one, the value here, and he firmly established two things. One is that it's a very compact object, number one, and number two, that it is that Einstein's prediction was quite right. Just 1 gram per centimeter cube, and the density of air in on the Earth in the atmosphere is far lesser. Now we believe now, though that was again not completely established in the early days of the 20th century, early years of the 20th century, that this is really a star. Stars are made up of gas. So even though they are made up of gas, then is it meaningful to have a density as high as this? Can we still call it a gas, or would it become a liquid or a solid or some other such material? So that those are the very perplexing questions that one has got to answer. And the answers actually, once you understand the physics, turn out to be quite nice and elegant and simple. But they led to a lot of confusion in the old days. So then what happened was that around this time that you are making his measurement, that was the time when Fermi-Dirac statistics was discovered. Okay, so Dirac and Fermi did it independently. Okay, and then immediately after that, William Fowler, who was a theoretical physicist in Cambridge, and he applied Fermi-Dirac statistics and showed that you could understand the behavior, the properties of white dwarfs with the application of these statistics. Okay, so that was a very great progress which was made in the understanding of white dwarfs, and moreover, it was also great progress in astrophysics itself. Right. So then, then came Chandrasekhar, who established that there is a maximum mass limit for white dwarf, and again taking astrophysics in completely new directions. Right. So we already are in extremely interesting territory, and so you see here, series B, the properties, and you will find that the it is the radius. No, there's something wrong here. Yeah, the temperature, the radius should be like this, much smaller. Yeah. So this is no, this is right. This Sirius A. So you find that it has got a mass of 2 solar masses, and then a radius of 1.7 times the radius of the sun, and high luminosity. Now Sirius B, if you look at the modern values, so you find that the temperature is as high as 35,000 Kelvin. Its luminosity is very low, and this luminosity is about uh, 10 to the minus 3 times the luminosity of the sun, 10 to the minus 2 times the luminosity of the sun, that's 3 times, and then you look at the radius, and which is about 0.01 times the radius of the sun, so which is 10 to the minus 2 times. Please remember that number. Okay, they are very useful numbers. And so if you actually take the mass of the sun and divide it by the volume, then you will find that the density of the matter in the sun is like 1.4 grams per centimeter cube. So if this one is 10 to the minus 2 times smaller, uh, then it would mean that the density is 10 to the 6 times bigger. Because as you know, the density goes as 1 upon r cube. So this is an extremely dense object, much more dense than these early estimates gave you. All right, so how does the size of the white dwarf compare with the size of normal stars? So, so you see here, then here is the most normal star that we know, which is our sun. And then on the one hand, on the one side, you've got the red dwarfs, the smallest stars that you can have. So this has got 1 solar mass, which is 2 into 10 to the 33 grams. And then there's a lower limit of mass about 0.08 solar masses. You can't really have a star with mass less than this, because the central temperature turns out to be too low to ignite the conversion of hydrogen to helium. Right? So therefore, this is an absolute lower limit of the mass of a star. As you go here to the right, then the masses can get bigger, and we know stars with 150 solar masses. Stars with much larger masses also have been theoretically considered, for example, by Hoyle and Fowler, but they are not yet been observed. But one limit which comes in for high mass stars is that the pressure of the radiation in them becomes so high that the star can just get blown off. That is, so there's a maximum mass which is not the Eddington limit. And then you've got these very large stars, which are called the red giant stars. Well, these are not very massive or anything, but they're simply they're stars in late stages of stellar evolution. Okay, so here you've got a radius of 700,000 kilometers, and in this range, about 0.1 to 10 times the radius of the sun, here up to 50 times the radius of the sun, and here you've got 1,000 times the radius of the sun. Right, so these are all large objects, and what happens to white dwarfs then? We have seen that this got a radius of about 6,000 kilometers. Mass is approximately the mass of the sun, and compare that with the Earth, which has got more or less the same radius. Okay, and then the Earth has got a mass of about 3 into 10 to the minus 6 solar masses. Okay, and then you've got a neutron star here, and so the neutron star, which I probably will not be talking about, is it has got a mass again comparable to the mass of the sun mainly. The radius is only 10 kilometers. Right, so these are a white dwarf and a neutron star. They are not really stars. They are object. The white dwarf is a degenerate object, and neutron star is a degenerate object made up principally of neutrons. Okay, and then of course there's a black hole here. And the picture of a black hole, you don't see the black hole at all because it has got exactly zero size, and then it also is quite invisible by itself. So we'll see about that later. Right. So now, how do the densities compare? And I'm giving you all these heuristics because it helps to settle ideas in your head. So, so the mass of an elephant, Indian elephants are smaller than African elephants. What you see is the African elephants, they're a little bit heavier. And then you find that it has got a mass of about 1 ton. And that is exactly the density of a white bar, 10 to the 6 grams per centimeter cube. Okay, that is 1 ton per centimeter cube is the density of a white bar. Right? The density of a neutron star, take all the people on Earth, put them in one pan, and then one spoonful of neutron star matter would have the same weight. So 5 to 10 to the 14 grams per centimeter cube. Okay, and a black hole, of course, the density goes to infinity and you get a space-time singularity. Well, so let us quickly recapitulate these things because they are going to be very useful in what I go into now after this. The sun, I already mentioned the mass, the radius. I like CG. I remember them in CGS units, which are completely outdated. Then the density is 1.4 grams per centimeter cube. And here's what is called the total energy, which is the sum total of the thermal energy of the object and the gravitational energy. And as you know, the gravitational energy is approximately equal to minus g m square by r, and so that is negative. So the total energy, because it's a gravitationally bound object, the sun, like these other objects, are gravitationally bound. The total gravitational energy is negative, minus 2 into 10 to the 48 Earth. The fact that it is so large is again important in the formation of some supernovae that I'll be describing to you. A white dwarf, more or less the same mass as the sun, typical white dwarf, and we have seen the radius is 10 to the minus 2 times the radius of the sun. Density is a billion times the density of the sun, and the binding energy is now minus 2.4 10 to the 50 ergs. And then for neutron star, 1.4 solar masses, radius 10 kilometers. This is the density, and the binding energy is 10 to the 53 ergs. And which is why when you form a white dwarf, you get a planetary nebula, and when you form a neutron star, at the end of stellar evolution, you get a supernova. And that is because so much energy is released from the object. Okay, and then this is probably last slide in this series. So what you have got here is a white dwarf mass radius relation. Now here on the on the x-axis we have got the mass in logarithmic scale. On the y-axis we have got the radius of the object in the logarithmic scale. And then you will see here a rough proportion. These are normal stars. These are not white dwarfs, just normal stars. And you see a rough proportionality. So which means that roughly speaking, the radius of a star like the sun is proportional to its mass. So if you take a star which is twice as massive, the radius will be approximately twice as much. If it is half as massive, the radius will be half as much. In the case of white dwarfs, you see exactly the opposite relation, which means that the more massive the object, uh, the less is the radius. And this is quite counterintuitive, right? Because if you go on adding mass, you expect the object will get bigger. Here you go on adding mass to the white dwarf, then the white dwarf actually gets smaller. And that is because the physics here is essentially governed by quantum mechanics. So even though it is an object of stellar size, of stellar mass, the physics is because a fully degenerate object. And that is what leads to all these counterintuitive reasons. Right, and then I should mention here before I go into uh, actual development of the physics is Chandrasekhar's equation, and because that is how this particular cycle of understanding white dwarfs more or less ended, is that white dwarfs have a maximum mass. Okay, so he called it a critical mass, we call it the Chandrasekhar mass, and its approximate value, which I will derive for you, is h cross c upon g mp to the 4 by 3 raised to 3 by 2. mp is the mass of the proton. So you see that this is something quite magical, this relation. Okay, that is because on the left hand side, and its value is about 1.4 solar masses. So on the left hand side, you have got an astrophysical object. Okay, so and so you're talking of stars, mass of a star. On the right hand side, you have you just have physical constants, right? So in fact, it's quite possible for you to use units in which h, c, and g are equal to 1, and therefore m Chandrasekhar is simply m raised to 4 by 3 to 3 by 2. It's just m, the mass of the proton to the minus 2. That's all. What it tells you is that this is an incredibly profound result. Means that absolutely, there is no such thing as getting it wrong. Result is there, and you will see is that you introduce new elements. For example, you introduce a magnetic field or something like that, and then which adds to the physics and which changes the value of the threshold mass. Right. So this is really one of the most beautiful equations that you'll come across. So now we go into the theory of white dwarfs, and again I'll take you through different ways of doing it, and then maybe the next time I'll put on a few more formal relations for you. But let's first understand the physics of white dwarfs. So I don't know whether it's all right to take questions here. Does anybody have any questions at this stage? Okay, I can see that there's already one question here. No, does anybody have? I'll explain. There's a question here which I'll be talking about. Uh, does anybody have any simple question now? What is it? There's one question here which says from Rashmi Sahu. It says the distance from the Earth of Sirius A and B. Are you asking me what is the distance? Yeah, I'll tell you that. I have forgotten. But I'll tell you that in a moment. Okay, um, I'll tell you that a little later. What would happen if we add more mass to the white dwarf star, more than the Chandrasekhar limit? I'll come to this toward the end of my lectures. What is the difference between planetary nebula and supernova? Okay, a planetary nebula, you see that when a star comes to the end of its life, it implodes, forming a white dwarf, providing its mass is small enough, and then the outer layers are thrown out in a violent explosion. It's called a planetary nebula. It's called a planetary nebula. Planetary is just a name. In the early astronomers, or using very small telescopes, thought some of these were planets because they happen to have extended size. Okay, but they're just a name. And a supernova is that when the mass of the star is large, larger than 8 solar masses roughly, then when it collapses, it forms a neutron star or a black hole, and the outer layers are thrown out in a very large explosion, which is known as a supernova. How could you? Somebody is asking me how to find the angle of inclination of white dwarfs. You see, you can't really find the angle of inclination, but what you can do, look at it this way: just imagine that you have got a circle, right? And then let's take the normal to the circle, and let that normal be in a line of sight. Then you'll see the circle as a circle. But imagine that the normal is not along the line of sight, but is making an angle to it. Okay, then you can easily prove that the circle should appear like an ellipse. Okay, so then if the angle is 90 degrees, the ellipse will degenerate into a straight line. Right? So if you know that the orbit is a circle, then if it appears elliptical, then you will be able to say that the inclination angle. But the point is you can't really do that because the orbit, the orbit of the Earth around the Sun is not really a circle; it's an ellipse. So that is the problem. So finding an inclination angle takes a lot of work. Okay, I'll continue with my lecture now. Oh dear. Yeah. So you see that now I'm going to go to the theory of white dwarfs, but I need here. Uh, I want to talk to you about the equation for hydrostatic equilibrium. And if anybody is doing the theory of stars for you, they definitely have done this equation, which is an incredibly simple equation, but which gives you a lot of insight into stars. So you see that if you look at a star like the sun and take a small little piece of it. So first of all, the sun is in hydrostatic equilibrium. What it means is that it maintains largely the same size for billions of years. Now, it is not as if when I say the same size, it doesn't mean that the surface of the sun is a hard surface, like the surface of a rocky planet. It is very diffuse, there are all kinds of things coming and going, but you can define a size in various ways, and that remains perfectly constant. So, and how does the size remain constant? Is that you take a small piece of matter in the star, and then you will find that this has got two forces mainly acting on it. One is the force of gravity, which tries to pull in this matter, the piece of matter, towards the center. And then there is the outward pressure. And this pressure is thermal pressure, meaning that because you know that the interior of a star is very hot, and therefore it will have very high pressure, and therefore there's a net outward force on this element. And then the fact that there's hydrostatic equilibrium means that these two forces must balance each other, not only at this particular point, but at every point in the star. So when you take that into account, it's just a 3-line, 4-line derivation, and you get this beautiful looking equation, which is that dp by dr, where the p is the pressure, r is the distance from the center. So this is the gradient of the pressure, that is equal to minus g m. M is the mass, is the mr, meaning that this is the mass. So if this is at a distance small r, then draw a circle of small r around the center, and m is the mass which is contained in that. Okay, and rho is the density at that point, and r is the distance from the center, of course. So dp by dr is equal to minus g m rho by r square. Now, you clearly can't solve this equation as it stands because the number of there is because there is the first order equation, and then but the number of variables is p, there is rho and r. So you need all kinds of relations between them. When you try to introduce the equation of state, then you bring in the temperature, and that is how astrophysics becomes very complicated. But this equation is going to be important for our considerations here. And let us see one simple, very important conclusion that leads us to is that you see, if you look at dp by dr, which is the gradient here, uh, I could uh, I could approximate dp by dr by the total change in pressure, the pressure at the center minus the pressure at the surface, which is taken to be 0. So that is Pc divided by R. R is the radius of the star. So you're approximating the gradient by Pc by R. Right? And then we approximate the density. We take the average of the density, which is now the total mass of the star divided by the total volume, which is 4 pi by 3 R cube. Right? So if I substitute these two quantities here, then I'm dropping the minus sign for now, and then you'll see that you get an expression for the central pressure, which is the central pressure is g m square by r to the fourth. Right. So this is actually a remarkable result in the sense that. Uh, but let me first go to the next step and then tell you why it's so remarkable. Now I'm dropping the c also here. So you see that what is the pressure? I can put on the pressure because can be considered to be an ideal gas with excellent approximation. You can P is equal to nkt. There's a simple gas equation. N is a particle number density. Now, if I assume that the gas is made fully of hydrogen, then the particle number density can be put as the matter density divided by the mass of the hydrogen atom, which is equal to the mass of the proton, because the mass of the electron is so much smaller than the mass of the proton. So I got the relation P is equal to rho kT by mp. So if I put it all together, then I'll get a temperature at the center, Tc, is approximately equal to gmmp by kr. So now you'll see that this is already a very familiar equation. And then if I take this is m, this is the mass of the proton. I know about the mass of the proton. I can normalize the mass and the radius to the mass and radius of the star, of the sun. And then I put in the constants and I'll get the beautiful relation that the temperature at the center is approximately equal to 2 into 10 to the 7 Kelvin uh, by m by m solar, r by r solar. So for the sun, it is indeed about 20 million Kelvin. But if you give me a star which is 4 times massive, I can put that number here and get the temperature at the center. So why is this such a profound conclusion? That is because you see that I have no access, I have no direct access to the interior of the sun. But nevertheless, by measuring the mass of the sun, which I can comfortably do from the earth, and the radius, which again I can comfortably measure from the earth, I'm actually estimating the temperature at the center of the sun just using this equation of hydrostatic equilibrium. And that is how you can make progress towards understanding very complex astrophysical objects. Now just look at this equation here. P is approximately equal to gm square by r to the 4. I can write this as P by m is approximately equal to gm by r to the 4. And I'm going to use this in the calculations I'm going to do. All right. Then now let us look at what is known as the Maxwell-Boltzmann distribution. So you see that when you look at the interior of a star, as I told you, if you look at the sun, the temperature inside is like 15, 16 billion Kelvin at the center, and then on the surface it is about 5,800 Kelvin. Because if you look at the yellow color of the sun, then just by applying Wien's displacement law, you could say that the temperature is about 6,000 Kelvin. But there's a way, something called the effective temperature, and that is defined in various ways, and then that is a good measure of the temperature at the surface, and there were like 5,880 or something like that, a formal number. So which means that the temperature is low outside and high inside, but as you go inside, the temperature becomes higher and higher and higher. At any given point of the star, you can assume that there is thermodynamic equilibrium. You see that by definition, the star is not in thermodynamic equilibrium totally. Because if it were, then as much energy would have to go into the star as is coming out of it, which is not happening. None of us would exist if there was no net energy coming out of the sun. So it is the energy which is flowing from the inside to the outside. But what is most important is that the energy which is leaving the sun is exactly equal to the energy which is produced inside. Because if there were an imbalance, if some energy remained inside, then some would quickly get hot and hot and hot and explode. And so now, even though it is not in thermodynamic equilibrium, one can assume that small portions of it are in thermodynamic equilibrium. And when you do that, then you can apply your usual thermodynamics. So there is a Maxwell-Boltzmann distribution, because at any given point I can assume that the temperature T. Then the number of electrons. I'll always be referring to the number of electrons, but you know that even if you assume that the sun is made up of pure hydrogen, then there will be as many protons as electrons, because matter is electrically neutral. It may be fully ionized in the interior. Protons and electrons are separated, and they are in equal numbers in the large. But we don't consider protons because, first of all, you can stick them in, and second, you'll find that when you talk of degeneracy, it is the electrons which become degenerate. I'll explain these concepts again as we go along. So, if you consider the number distribution of electrons with momentum between P and dP in a small volume dV, okay, then it is given by this particular expression, which is the Maxwell-Boltzmann distribution, e raised to minus p square by twice me kt, and then another p square here. So if you give the temperature, I can plot this distribution, and then you'll see here that the distribution is it has got one maximum, and the maximum momentum occurs at square root of twice me kt. Okay, these are all well-known results, and kinetic energy of the particle is 3 by 2 kt. So you see that the average kinetic energy of the particle is independent of the mass of the particle. This is what we call equipartition theorem. And then so therefore, if I considered protons here, again I would get exactly the same average kinetic energy. At the pressure P, you can show that the pressure is equal to nkt, which I can write as rho kt, because n is the number of particles. If it was simply a hydrogen plasma, it would be rho by mp. But the sun, for example, has got about 75% hydrogen, about 25% helium, and there's a small fraction of the heavier elements, which are all known as metals, which are present. So I cannot take all the particles to have the proton mass. For example, a helium nucleus of helium would have 4 times the proton mass, roughly speaking. So you take that into account by introducing the concept of molecular weight. Right. So the particle number density can be written as the total density divided by the molecular weight into mp. To be exact, this has to be written as mu, which is the atomic mass unit, and which one can also write as rho RT by mu. Okay, where R is the gas constant, right? And this is what is called the ideal gas equation of state, which applies excellently to the gas in stars. But we will see that the story of the white dwarfs is that this equation does not apply to them. But I want to show you why it does not apply to them. Right. So please, these are going to be very important for our reference. But these are equations with which I'm sure all of you already are very familiar with. All right. So so now let's consider an atom. Okay, an atom in general consists of protons and the neutrons in the nucleus, and then you've got these electrons which are going around. Right. So and it was established by Rutherford that the nucleus, which consists of the protons and neutrons, is very much smaller in size than the total extent of the atom. So, nuclear size is much smaller than atomic size. And how much is atomic size? It is the sort of what you call roughly the Bohr radius, which is 5 into 10 to the minus 9 centimeters, and this is the thing. And then the nuclear radius is about 10 to the minus 13 centimeters, right? So, so this is the these dimensions are going to be very important for our argument. Right. So now let us look at the concept of uh, interparticle uh, separation. So what do I mean by that? Is that if I give you an object with mass m and radius r, we already considered this many times. Right today, rho is given by this particular expression here, and I can take n to be rho by mp. I'm just going to drop mu because it's not important to the arguments. Rho goes n goes by rho by mp, which is 3m by 4 r cube mp. So if I give you uh, a gas with a density like that and ask you what is the average interparticle distance? Means what the distance between any two particles in the gas? As all of you know, the particles are moving around incessantly, and the distances between any two particles will keep changing with time. But you see that the gas is in equilibrium, right? And therefore, the density, average density anywhere in the gas should remain more or less the same. Now, if I increase the density somewhere artificially, for example, if I clap, then the density in the neighborhood will go up. Okay, so then that quickly gets diffused out. Okay, so it damped up. So then you'll have the average density. So when you're going to the average density, what is the average distance between particles? And then the contention is that the average distance between particles is simply n to the minus 1 by 3. Okay, so it is very easy to understand it by looking at the diagram here. And it's a very important concept is that this is one particle. And let's say the next particle is somewhere here. So what I do is that I draw a circle around this particle. I draw a circle around this particle so that there is only one particle in it. So when the circle is small, it will be true that will make circle bigger and bigger. And then when I make it sufficiently large, I'll meet one more particle. Right? So here, this is the, let's say, the maximum L for which there is only one particle in the circle. Okay, then because n is the number density of particles, L cube is the volume of this one. Forget 4 pi by 3 because there's a cube here. So therefore, by definition, n into L cube is approximately equal to 1. Okay, which would mean that L goes as n to the minus 1 by 3. So this is a extremely useful mnemonic for quickly looking at the distances between particles given the density. Now let us look at this relation in practical circumstances. So you see that we are doing astrophysics now, and not only stellar astrophysics, so which means that you're talking of 2 into 10 to the 33 grams and so on, we always normalize it to the sun. So if I take this equation and normalize it to the sun and introduce all the constants, I like to do this on the board by actually introducing the constant because that fixes ideas in your mind. Unfortunately, that is not possible at the present time. So when I put in these constants like proton masses, and then you see what I get is L is approximately equal to 10 to the minus 8 into m by m solar to the minus 1 by 3. It is just this minus 1 by 3 and r, because r to the r cube in the denominator and minus 1 by 3 gives me an r. So I have normalized it to the solar mass and the solar radius. And then what do I get here? So for the sun itself, m is equal to m solar, r is equal to r solar, and the interparticle distance turns out to be 10 to the minus 8 centimeters. Right? That is because so what does it tell you about the density? If I tell you that the interparticle density 10 to the minus 8, okay, then what is the density of particles? It is inverse cube of this. Right? So that is 10 to the 24 per centimeter cube. Okay, so if I say that, so tell me what is the mass then? So what is the mass density? Let's just imagine the sun is made up of protons. Okay, in the mass of each proton is how much? 6 into 10 to the minus 24, 1.6 into 10 to the minus 24 grams. So the inverse cube of this is 10 to the 24 and multiply to the mass of the thing and you get a few grams per centimeter cube, which as you know is indeed the density of the sun. So we're on the right track. Okay, so in particular, if I if I showed you in the last uh, thing is that the bore radius is 5 into 10 to the minus 9 centimeters, right? So what happens is that for the distance between the particles in the sun is equal to the bore is actually greater than the bore radius. Okay, and then in the case of but if I go to a white dwarf, okay, if I go to a white dwarf, you'll see that the mass is more or less the same as the mass of the sun. The radius, as I repeatedly told you, is 10 to the minus 2 r solar. So this becomes 10 to the minus 2. This becomes 1. And therefore, L becomes 10 to the minus 10 centimeters. And you see that now less than it has become less than the Bohr radius. Okay, so but it is less than the Bohr radius, but it is far bigger than the nuclear radius. So what does this tell you? Okay, it tells you that as you just imagine taking an object which has got an average density of 1 gram per centimeter cube. Let's say it has got a total real density of 1 gram per centimeter cube. Then let's say that made up of hydrogen. Let's suppose that the temperature is not too high. Then you'll have these hydrogen atoms with each atom consisting of an electron going out a proton. But if I start squeezing it, and if I go on increasing the density, then the atoms will move closer and closer to each other. Right? So then if I approach white dwarf densities, then what it would mean is that the distance between two particles, okay, actually is becoming less than the Bohr radius. Now that really is not possible for normal neutral matter because you know that you've got an electron going out the proton, but then if two hydrogen atoms come very close to each other, then there is no such thing as the electron going out the proton because the potential of the neighboring protons come into the cube. So what will happen is that the matter cannot exist in the form of electrons and protons. So therefore, it means that this is something which is called pressure ionization. As you increase the pressure and bring the particles together, then the atoms lose their existence. That is gone. And what you will get is actually ionized gas consisting of protons and electrons. Right? So we are already quite far from the comfort zone, and not only there, and then the average distance between the particles is very small. Right. So now I've done my time. I'll stop here. But please remember these important results. Is that if you have the density that you get in white dwarfs is not compatible with the existence of unionized atoms. I mean, the matter must be completely ionized. And this was already realized by Eddington a long time ago. Now, being completely ionized is not such a big surprise because, for example, the temperature at the center of the sun and in the central regions in general is extremely high, and therefore you get just ionization because of the high temperature. Right, so now we will, the next time I will take this forward and show you why this necessarily implies uh, that you need to use quantum mechanics for the analysis. All right, thank you very much. Yeah, so I can find one question here which says, do white dwarfs mainly lie in groups surrounding each other? So that is not true. And you can get, I showed you the picture of a cluster of white dwarfs. That is because it was what's called a globular cluster. A globular cluster consists of up to 1,000,000 stars. And then, so which are all, so as they evolve, as they form white dwarfs, so you'll get a cluster of white dwarfs. But the sun, for example, is not a part of a cluster as such. And so when the sun finishes its evolution, it's going to become a white dwarf, which will be an isolated white dwarf. Now, why do we express uh, the temperature in terms of solar mass and radius? Can't we directly substitute the known values to get a simplified expression? No, you can't. You see, you need to get used to these kind of expressions because uh, if I tell you that, look, I got an object which has got seven solar mass, and three solar radii, and what is the temperature at the center? So if you just go on putting the numbers and then you do the calculation, it'll take you some time. But if you look at the equation I wrote down, you can just substitute for you put seven, you put the thing, and then you will immediately get the number. So these are extremely useful in making quick estimates of important parameters. Is there any limit for the size also? What do you? I don't know what is meant by the limit size also. But in what context is this being asked? For dwarf star? No. What happens is that in general for a star, uh, it is there is a limit to mass, right? When you see for a star, it turns out that the mass of the star is overwhelmingly important property. So if you tell me that a mass of a star is seven solar masses, and then it is on the main sequence, then I can work out almost all of its properties, like size and thing, everything is digital. Only other unknown would be uh, what is the chemical composition, meaning that is it a pure hydrogen star or is a hydrogen? There's no such thing as a pure hydrogen star because if you believe in the Big Bang, then you produce a lot of helium in the Big Bang. So each star, even the earliest stars in the universe will have hydrogen and helium, and then the later stars would have heavier elements. But the chemical composition has effect, but not too high an effect. So that is why we only talk of the mass, and that determines the radius and so on. Yeah, so I always forget to do this, is to provide you with a set of references, uh, the things that you could read, and I'll do that in my next lectures. But actually, it is not very easy to find the kind of material that I'm doing here because I've been teaching this for a long time and I keep putting it up. And every time I give a talk, I revise it. Like the whole morning, I was revising this. So, but I can lead you to books which are very useful. For example, there are two books by G. Srinivasan. Srinivasan is a very senior Indian astrophysicist, and there are two books. One moment, there's one somewhere here. Yeah, and one book is called "What Are the Stars," and the other book is called "Can Stars Find Peace?" And they are both quite reasonably priced books, 270 rupees, if they're still available. And you should try very hard to get hold of these books and read them. But there are also other more regular texts which I'll give references to. Okay, there are no further questions. So, Santosh, are there questions coming in through any other route? Can you just read them? Yeah, please. Yeah, yeah. I don't understand what you mean by nuclear pasta. Made of nuclear pasta. They're made of nuclear matter. I don't understand the word pasta. Dense object is universe. So what is the nuclear pasta made of? I mean the nuclear matter is made up of just neutrons mainly. Okay, so I'm sure that there'll be people who will be talking to you about neutron stars, and they will talk to you about.
Yeah, I will also be talking about nuclear pasta physics.
Yeah, yeah. What are the most recent observational results on the maximum mass of white dwarfs? No, I mean there is no such thing as most recent maximum white of. I mean you really have not you never have found a white dwarf with a mass greater than the Chandrasekhar limit. And in fact, it is very crazy that most neutron stars whose masses were measured were also of that kind. Okay, that remains true now, except that more massive neutron stars have also been found, and particularly, uh, yeah, in the LIGO things. Now, can you please explain the concept of degeneracy pressure? I'm going to do that tomorrow. In fact, that is the core of my lecture. If white dwarfs are not undergoing fusion, how are they radiating? The short answer is that they are just radiating the stored thermal energy. Okay, so they are very hot objects, even though we'll approximate them as t is equal to 0 objects, but actually quite hot, and they're just radiating out their stored thermal energy. I'll be talking about that. All right. Okay. There's Safiq CA raised hand. Last question.
Sir, how to find the mass of how to determine the mass of a white dwarf star? Normally, for main sequence stars, we calculate it from luminosity.
No. So you see, the thing is that you don't calculate it from the luminosity. If you know the luminosity, then you have got some rough indicator of the mass. And masses are actually have to be determined observationally if it is a part of a binary system. Now, if it is not, then there are several indicators. And for example, you could study for a main sequence star, you could study the spectrum in detail. And then there are all kinds of relationships which are known, which are interpolations of observed values, which can indicate the mass. So for a white dwarf, again, those kind of indirect indicators are there. But otherwise, you have to depend upon it being a part of a binary system, for example. And there are many, many of these available. Yeah. Yes. Prevalent what? Can you put the question in the thing? Okay, okay. Okay, there it is. No, I'm sorry, I don't understand what is being said here. And we can do that offline sometime. You can send me an email or something. I don't understand this question at all. Okay? Thank you very much then. I'll stop here. Bye.